Hi, my name is Krzysztof Buczak and I'm a software engineer at Containerised. Today, let's explore the power and value of containerization in RDK-B. Think of a container as an environment that is separated from the main system. It can be considered a simple standalone system running inside the host. When you run RDK-B on your device, it operates on resources such as hardware, the kernel, and the root file system. To utilize these resources, your system manages them and assigns memory, processor time, hardware access, and more to each process. Moreover, for a specific process to run, it's crucial that all mandatory dependencies are met, meaning that in the file system there are libraries, configs, directories, and applications that the process is going to use, preferably, in the case of libraries and applications, in exactly matching versions. A container can, or when it comes to kernel even must, share some resources with the main system, but it operates independently in terms of process and memory management. It may also have an entirely unique root file system. This allows the container to have, for example, a completely different set of libraries and their versions. As we will discuss in detail in a moment, a container's access to the host system is constrained to enhance security. Let's take a look at some of the biggest advantages of containers. From operators' point of view, the most important feature of this technology might be security. Containers offer a secure, isolated environment that protects the host system from crashes or vulnerabilities in individual apps. Thanks to sandboxing the applications, containers have constrained access to system resources and reduce the risk of system-wide compromise. If things go wrong and your app crashes badly, in the worst-case scenario, it will crash the container, not the host. Your RDK-B system will continue working just fine. Also, updating a container is safer than updating the host file system. If the update introduces dependency issues or bugs, again, this will only affect the container, while the host root FS remains untouched. Flexibility is also a crucial feature of containerization. Imagine that you have an application that requires a specific legacy version of Python, but everything else on your main system runs on a newer version. If the old version is only used by this one app, it's not recommended to install it for the whole system. Doing so could create conflicts or provoke security breach. A container is the perfect fit for this situation. To keep it lightweight, it can mount most of the host file system, but provide its own version of Python. For other app-specific dependencies, we can provide them accordingly. Moreover, containerization simplifies updates and rollbacks, minimizing downtime and security exposure. With the power of containers, you get built-in resilience and enhanced control over your software stack. And when you uninstall the container, you don't have to worry about leftovers. As they are self-contained environments, they leave no undesired dependencies in the host file system. To understand containers better, let's also look at the concept of LCM, which stands for lifecycle management. The LCM processes define principles for the end-to-end management of applications or services running on the RDK-B platform. In the context of containers, this process must address essential functionality such as installing, activating, upgrading, deactivating, and uninstalling containers. Containerization and lifecycle management are implemented in RDK-B with the DAC distro feature. It's a set of components that secure and control access to device resources. DAC implements whitelisting and blacklisting of executables and services and enforces policy-based access control at runtime. It also takes care of versioning, rollbacks, and lifecycle management. With DAC enabled, the system is equipped with two key components, DSM and Dobby. DSM stands for Device Software Module. This component manages software updates and related lifecycle operations such as scheduling, rollback, and version reporting. Dobby, or Docker-based thingy, is used for managing and running OCI containers, where OCI stands for Open Container Initiative Specification. Dobby component takes care of sandboxing RDK components and apps. In other words, you can think of DSM as a package manager, while Dobby is the engine that runs the packages. With this knowledge, let's take a look at a typical LCM workflow in RDK-B. First, a cloud service, e.g. a controller like ACS, sends an install or upgrade command. Then, DSM downloads and deploys the container. Containerized apps work in an isolated environment, independent from the host. After successful deployment, Dobby maintains the state of each application. It can be running, idle, etc. If an update is needed, it can be triggered via the cloud service and handled by DSM. If the updated version of the app doesn't work as expected, DSM can perform a rollback to the previous working version without affecting the rest of the host system. When the container is no longer needed, for example, if you want to free up space for other components or containers, it is deactivated and uninstalled by DSM through the appropriate request. Containerization is an enabler for software modularity to manage device software more efficiently and enable new value-added services. The possibilities of containers are limitless. Firewalls, ad blockers, smart home controllers, or even antivirus software built into the broadband router are not a distant dream. They are already happening. Containers are not limited to cutting-edge hardware. They can also enhance your legacy devices and upgrade us to more capable smart routers. Containerization offers countless opportunities. Are you ready to unlock them? You can do it with us. At ConsultRed, we specialize in software development and integration for broadband and media solutions and much more. Want to learn more or work with us? Be sure to get in touch. We would be happy to collaborate with you on your next project.